What if everything we think we know about the universe is built on a fundamental misunderstanding? We often picture the cosmos as a vast, silent void, a container with edges that mark the end of space and time. But what if those edges aren't in points at all? What if they're not limits, but creators? Imagine for a moment that the boundaries of the universe are actively weaving the very fabric of time itself. This isn't science fiction, it's a revolutionary idea emerging from the frontiers of cosmology, one that invites us to completely rethink the nature of reality. For centuries, humans have looked at the stars and wondered where it all ends. We've drawn maps of the cosmos with borders and horizons, imagining walls in the void. But what if we've been asking the wrong question? Instead of asking what lies beyond the edge, perhaps we should be asking what the edge is doing. Could it be that time, the steady, irreversible flow we experience every moment, is not something the universe simply has, but something it generates right at its outermost reaches? This shift in perspective doesn't just change how we see the cosmos, it changes how we see ourselves within it. In this video, we're going to explore one of the most profound mysteries of modern science: why the universe's edges could be creating time instead of limiting it. We'll journey through mind-bending concepts like the holographic principle, entropy, and the arrow of time, uncovering how these ideas intersect to form a new vision of reality. You'll discover how black holes, quantum fluctuations, and the accelerated expansion of space might all be clues pointing toward a cosmic engine humming at the boundaries of existence. By the end, you won't just see the universe differently, you'll feel time differently. So settle in, open your mind, and get ready to question everything you thought you knew about the nature of time and space. Think about the last time you looked up at a clear night sky. You see a vast expanse of stars, and it's natural to wonder, where does it all end? For most of human history, the answer to that question has been rooted in a simple, powerful idea that the universe has a boundary. A final wall, an ultimate limit. This traditional view paints the cosmos as a kind of magnificent, but ultimately closed container. Its edges are the absolute end of the road for space, for matter, and even for time itself. This concept is deeply ingrained in our thinking, from ancient myths about the edge of the world to the most sophisticated models of modern science. Aristotle imagined the universe as a set of nested crystalline spheres, with the outermost sphere marking the absolute boundary of creation. Centuries later, even Isaac Newton, who gave us a universe of infinite space, still saw it as a static stage with fixed properties, a container whose walls, even if infinitely far away, defined the rules within. This perspective is incredibly intuitive. It gives us a sense of order and containment. We talk about the observable universe as a sphere centered on us, with a horizon roughly 13.8 billion light-years away. Beyond that horizon, we say, we cannot see because light hasn't had time to reach us since the Big Bang. That language itself frames the edge as a limit, a barrier to our knowledge and exploration. It suggests that the universe is, in a fundamental way, finite and bounded. This view inherently limits possibilities. It implies that everything that can happen must happen within these confines. It suggests that time, too, has a beginning and will have an end contained within this colossal box. But what if this intuitive picture is misleading us? What if our focus on boundaries as simple limits has caused us to overlook their most fascinating potential? The very word edge conjures an image of something terminal and passive. A cliff face where reality simply stops, but nature rarely works that way. In almost every other field of science, boundaries are not where things end, they are where the most interesting things begin. The surface of a star, the membrane of a cell, the shoreline of an ocean, these are all dynamic interfaces where energy is exchanged, information is processed, and transformation occurs. They are active, not passive. By clinging to the idea of the cosmic edge as a mere limit, we might be missing the real story. This traditional view, while comfortable, may be a profound oversimplification that prevents us from seeing the universe's true creative potential. But what if we've fundamentally misunderstood the nature of these cosmic frontiers? Instead of a final, silent wall, imagine the edge of the universe as something more like the surface of the ocean, a dynamic, churning interface where immense forces are constantly at play. This isn't just a poetic shift in perspective, it's a view supported by some of the most profound principles in modern physics. In nature, boundaries are rarely passive. They are almost always the sites of the most intense and creative activity. Think about the event horizon of a black hole. From the outside, it appears to be a simple spherical boundary, a point of no return. But delve into the physics, and you find that this horizon is a place of incredible energy and transformation, where the very concepts of space and time break down and reform in strange new ways. Particles and radiation can be generated there, a process that suggests boundaries aren't just limits, they're generators. This principle of active boundaries extends far beyond black holes. In the science of thermodynamics, which governs heat and energy, the boundaries between systems are where the real action happens. It's at these interfaces that entropy, the measure of disorder, flows and energy is exchanged, driving everything from the expansion of a gas to the beating of a heart. Without these active boundaries, change would be impossible. The universe would be a stagnant, uniform soup. So why would we assume the largest possible boundary, the edge of the cosmos itself, is any different? If we apply this same logic, the cosmic edge transforms from a cold, dead end into a vibrant and potentially creative membrane. It could be a place where the fundamental rules of our reality are not just contained, but actively written and maintained. This redefinition is crucial because it opens the door to a breathtaking possibility that the flow of time we experience, the relentless march from past to future, isn't a pre-existing feature of the universe but is instead being generated, moment by moment, at its outermost edges. The frontier isn't a limit, it might be the engine. This brings us to one of the most astonishing ideas in modern physics, a concept so radical it feels like it's straight out of science fiction, the holographic principle. To grasp this, let's start not with the cosmos but with a simple credit card. That little shiny strip on the back is a hologram. It's a two-dimensional surface, but when you tilt it, it projects a three-dimensional image. Now take that incredible idea and apply it to the entire universe. The holographic principle suggests that our reality, with its rich three-dimensional depth, including the passage of time itself, might be a magnificent projection from a two-dimensional surface at the very edge of everything. This mind-bending theory didn't come from nowhere. It emerged from a deep puzzle about black holes. Physicists discovered that all the information about what falls into a black hole, every atom, every particle, your entire history, seems to be perfectly encoded on its event horizon, its two-dimensional boundary. The implication was staggering. A 3D volume of space could have its entire description written on a 2D surface. If this is true for a black hole, why not for the whole universe? Our cosmic horizon, the edge of our observable reality, might not be a barren wall. Instead, it could be the ultimate hard drive, a vast, bustling repository of information that encodes everything within the volume it encloses. Every star, every planet, every one of us, and every moment that has ever been or ever will be, could be written into the data on that distant boundary. This completely flips our understanding of time on its head. We're used to thinking of time as a fundamental, internal river flowing through the universe. But if the holographic principle is correct, time might not be fundamental at all. It could be an emergent property, a side effect of how that information on the boundary is processed and translated into our experienced reality. Think of it like a movie. The entire film, from beginning to end, exists on the two-dimensional strip of the film reel. But when that reel is projected, we experience a flowing, three-dimensional story with a clear past, present, and future. In this analogy, the cosmic edge is the film reel, and our unfolding reality is the projection. The flow of time isn't something happening inside the movie. It's a consequence of the projector's mechanism reading the data on the reel. This suggests that time, as we know it, is not a primary feature of the universe but is instead generated or projected from its outermost edges, challenging us to question where and how our most familiar dimension truly begins. Now, let's connect this to one of the most familiar yet mysterious features of our existence, the arrow of time. Why does time move forward? We remember yesterday but not tomorrow. A broken glass shatters on the floor but never spontaneously reassembles itself. This one-way street of cause and effect is one of the most fundamental rules of our universe, and it's governed by a concept called entropy. Entropy is essentially the measure of disorder in a system. The second law of thermodynamics states that the total entropy of an isolated system can never decrease over time. It can only stay the same or increase. In simpler terms, things tend to move from order to disorder, from a neat stack of papers to a messy desk, from a hot cup of coffee to a lukewarm one as its heat dissipates into the room. This relentless increase in disorder is what gives time its direction, its arrow. But here's the profound puzzle. Why was entropy so low in the past to begin with? The universe started with the Big Bang in an incredibly hot, dense, and highly ordered state, a state of remarkably low entropy. For time to have an arrow, for the second law to even work, the universe needed this specific starting condition. It's like a wound-up spring. Time's arrow is the unwinding. For over a century, physicists have wrestled with the question of what wound up that spring. The answer might be found not at the beginning, but at the edge. What if the cosmic boundary is the reason entropy was set so low at the start? And what if it's the ultimate destination for all that disorder, acting as a sink that pulls time forward? Think of the universe's increasing entropy not as a random drift toward mess, but as a kind of flow. Energy and disorder have to go somewhere. In any system, gradients, differences in energy or concentration naturally try to even out. Heat flows from hot to cold. This flow is what drives change, and it requires a boundary or a sink to receive that energy. In your room, the walls absorb the heat from your radiator. On a cosmic scale, the ultimate sink for this flow of entropy could be the edge of the universe itself. If the boundary condition at the edge of the cosmos is one of maximum entropy, a state of final, total equilibrium and disorder, then it would create a powerful gradient. The entire interior of the universe would be perpetually flowing toward that state of maximum disorder, like a river rushing toward the ocean. This relentless flow is the arrow of time. This elegantly ties the microscopic world to the grandest cosmic scale. The reason your coffee cools and memories are only of the past isn't just a local rule. It could be a direct consequence of the universe's ultimate boundary. The edge isn't a passive limit we're expanding toward. It's an active participant, setting the conditions that orchestrate the irreversible flow of time throughout the entire cosmos. It's the reason the spring was wound up, and it's the reason it's unwinding in one specific direction. The frontier of the universe might be the silent conductor of time's symphony, ensuring the music only plays forward. To truly appreciate how the universe's edges might be crafting time, we need to venture into the bizarre and counterintuitive realm of the quantum. Even in what we perceive as a perfect vacuum, space is never truly empty. It is a seething, bubbling sea of potentiality, where pairs of virtual particles and antiparticles spontaneously blink into and out of existence in an energy loan paid back almost instantly. This ceaseless, frothing activity is known as quantum fluctuation, and it's a fundamental feature of reality at its smallest scales. While these fleeting particles usually vanish without a trace, their presence becomes dramatically amplified and consequential when they occur near a powerful boundary, like the immense gravitational edge of a black hole or, on an even grander scale, the very frontier of our cosmos. At these extreme interfaces, something extraordinary can happen. The tremendous forces present at a cosmic boundary can prevent these virtual particle pairs from immediately annihilating each other. One particle might be captured or pushed across the horizon, while the other escapes into the universe. This process, predicted by Stephen Hawking, is how black holes slowly evaporate, proving that boundaries don't just contain, they generate real, persistent particles from the quantum foam. Now expand this concept to the ultimate boundary, the edge of the observable universe. The conditions there could be acting on these quantum fluctuations in a similarly transformative way, but with consequences not just for matter, but for the very structure of time. The chaotic, probabilistic dance at the quantum level could be the raw material from which the ordered flow of time is sculpted at the cosmic edge. We already have a stunning precedent for this creative power in the very story of our universe's birth. The theory of cosmic inflation proposes that an unimaginably rapid expansion occurred a fraction of a second after the Big Bang. During this period, the entire cosmos was effectively a single, unified quantum field. The microscopic quantum fluctuations that rippled through this field didn't get smoothed out. Instead, inflation stretched them to astronomical sizes. Those tiny, random density variations became the seeds for all the large-scale structure we see today, the gravitational blueprint for galaxies, clusters, and superclusters. In this profound sense, the entire majestic architecture of the universe originated from quantum noise amplified during a period when the cosmos was, in effect, all boundary. This established link gives us a powerful framework for understanding time. If quantum fluctuations at a primordial boundary could seed all of space, why couldn't ongoing quantum activity at the current cosmic edge be seeding time itself? The periphery of the universe might be a constant crucible of creation, where these fluctuations don't just create particles, but generate nascent timelines or nudge the parameters that govern temporal flow. The steady tick of time we experience in the cosmos's interior could be the smoothed-out, large-scale result of countless quantum probabilistic events resolving at the boundary, much like the overall temperature of a gas is the average of countless chaotic molecular collisions. This perspective suggests time is not a monolithic, pre-existing river, but is more like a stream whose flow is continually fed by countless tiny springs at its source, the turbulent quantum springs at the universe's edge. Each moment we experience may be the distant echo of a quantum decision made on the farthest frontier, making the edge not a silent wall, but the most dynamic and creative workshop in all of existence. Now let's introduce another enigmatic player in this cosmic drama, dark energy. This is the mysterious, repulsive force that astronomers discovered less than 30 years ago, a finding so shocking it earned a Nobel Prize. We don't know what dark energy is, but we can see what it does. It's causing the expansion of the universe to accelerate. Galaxies are not just moving apart, they are flying away from each other at a faster and faster rate, stretching the very fabric of spacetime itself. This relentless expansion is directly responsible for what we call the cosmological horizon, the edge of our observable universe. It's not a physical wall, it's the ultimate limit of how far light can have traveled to reach us in the 13.8 billion years since the Big Bang. But here's where it gets truly fascinating. This expansion isn't just creating more space, it might be actively manufacturing time itself. Think of the universe not as a static container, but as a living, growing entity. With every passing moment, the cosmos gets a little bigger. New space is literally coming into existence between galaxy clusters. And if the universe is generating new space, could it also be generating new time? Some compelling theories suggest that these two acts of creation are inextricably linked. The process of cosmic expansion, driven by dark energy, might be the very mechanism that pulls time into existence from the boundary. In this view, the edge of the universe isn't a fixed line we're approaching. It's a dynamic and generative surface that is constantly moving, and with each new increment of space it creates, it also unfurls a new moment in time for the interior of the cosmos. The frontier is not a limit we will one day hit, it is a factory perpetually working. This turns our entire understanding on its head. We often think of time as the independent variable, the steady, universal clock against which everything else plays out. But what if time is actually a dependent variable, an emergent property that is a direct byproduct of the universe's expansion? The flow of time we experience, the relentless tick from one second to the next, could be the internal perception of the cosmos actively growing at its edges. It would mean that if the expansion were to stop, time might cease to flow in the way we understand it. Dark energy, therefore, isn't just a mysterious force shaping the structure of space. It could be the very engine of chronology, the hidden hand that winds the cosmic clock by stretching the frontier of reality. This concept forces us to reconsider time not as a fundamental stage on which the universe plays out, but as something more like a collective behavior, an emergent property that arises from countless simpler interactions. Think of it like the phenomenon of temperature. A single molecule doesn't have a temperature. Temperature is a property that only emerges when you have a vast collection of molecules jostling around, their average kinetic energy creating what we feel as heat. In a very similar way, time might not be a fundamental ingredient of reality but a large-scale consequence, a story that only makes sense when you have enough of the universe's basic building blocks interacting in a certain way. Some of the most ambitious theories in physics are built on this very premise. Take loop quantum gravity, for instance. This approach attempts to merge general relativity with quantum mechanics by proposing that space itself is not smooth and continuous but is instead woven from a network of tiny, discrete loops. In this breathtakingly minimalistic picture, at the most fundamental level of this spin network, the concept of time simply does not appear in the equations. It vanishes. There is no T for time. What we perceive as time is not a primary element but emerges from the changing relationships between these loops, from the evolving way this network connects and interacts. The flow of time is the flow of information and correlation across this cosmic web. Now, if time emerges from these underlying relationships, where in the universe are these interactions at their most intense and most defined? The most compelling answer points directly to the edges. Just as the surface of a pond is where the interaction between water and air creates waves and ripples, the cosmic boundary could be the primary interface where the fundamental relationships of quantum gravity are most actively negotiated and defined. The universe's edge might be the ultimate processing unit where the spin network's dynamics are crystallized into the orderly progression we experience as time. In this view, the frontier isn't just a place, it's a process. It's where the universe is actively performing the computation that results in the emergence of time for everything within it. This shifts our entire vocabulary about time. We move from thinking of time as a noun, a thing the universe possesses, to thinking of it as a verb, something the universe does at its boundaries. It's an ongoing activity, a continuous act of creation. The steady tick of seconds isn't a passive reading of some cosmic clock. It's the active output of a cosmic computer whose processor is the very edge of reality. This perspective doesn't diminish time. It makes its existence even more marvelous. It means that every moment we experience is a gift generated by the most extreme and dynamic processes at the farthest reaches of existence, connecting our most personal experience of the present directly to the universe's most distant frontier. To truly grasp how boundaries can forge the fabric of time, we need to examine the most famous frontier in all of physics, the event horizon of a black hole. This is not just an abstract line in space, it's a point of no return, a gravitational Rubicon where the pull becomes so intense that not even light can escape its clutches. For decades, we've understood this horizon as the ultimate prison wall, a one-way door into oblivion, but this simplistic view hides a far more fascinating truth. An event horizon is not a passive barrier. It is a crucible where the very laws of physics are stress-tested and rewritten, especially when it comes to time itself. From the perspective of an outside observer, time doesn't just slow down near a black hole's event horizon. It appears to grind to a complete halt. Imagine a brave astronaut on a mission falling towards a black hole. As they approach the horizon from our vantage point far away, their signals would stretch out, their movements would slow to an imperceptible crawl, and they would seem to freeze in time, forever etched onto the edge of the void. They cross the horizon, but we never actually see it happen. This isn't a trick of the light. It's a direct consequence of Einstein's general relativity, where gravity doesn't just bend space, it warps time. The event horizon is where this warping becomes infinite, making it the most powerful time distortion engine we know of. This bizarre time dilation is just the beginning. The event horizon is also a hotbed of quantum activity. As we touched on earlier, it's where virtual particle pairs are ripped apart, creating real radiation and slowly evaporating the black hole over eons. This process, known as Hawking radiation, proves that the horizon is not inert. It is dynamically interacting with the quantum vacuum, generating particles and processing information. It takes the chaotic froth of quantum possibilities and translates it into a steady, measurable output. In a very real sense, the horizon is not an end point. It's a transformational interface, converting one form of reality into another. Now, let's take this profound lesson from black holes and cast our gaze out to the largest possible scale, the cosmological horizon. This is the ultimate edge of our observable universe, the farthest distance from which light has had time to reach us since the Big Bang. We often think of it as a limit to our vision, a final curtain beyond which we cannot see. But what if it's more than that? What if it's an event horizon for the entire cosmos? Unlike a black hole's horizon, which pulls everything inward, our cosmological horizon is created by the outward acceleration of space itself, driven by dark energy. But the principle might be eerily similar. If a black hole's horizon can act as a generative surface for particles and a transformer of time, could the universe's own horizon be performing a similar function on a grand, all-encompassing scale? The conditions at this vast frontier could be just as extreme, serving as a constant source of quantum fluctuation and gravitational distortion. This immense boundary might be the primary surface where the information of our universe is encoded and processed, much like the holographic principle suggests. The steady, orderly flow of time we experience in the cosmos's interior, the reliable tick of the clock that allows for galaxies, planets, and life to evolve, might be the direct result of this processing. The cosmological horizon isn't just a limit we expand toward. It could be the active engine that is manufacturing the temporal order we take for granted, moment by moment. By studying these horizons, both the intimately small ones around black holes and the unimaginably large one that encircles us all, we learn a universal language of boundaries. They teach us that a horizon is never just an end, it is a beginning. It is a region of intense creative potential where the normal rules break down and new structures, including the very framework of time, are forged. The edge of the universe is not a cold, silent wall where physics gives up. It is the most vibrant and innovative workshop in existence, the engine of chronological innovation that makes our lived experience of time possible. We often picture the Big Bang as a single, dramatic explosion that marked the absolute beginning of everything: space, matter, and time itself. It's the ultimate starting gun, the moment the cosmic clock began to tick. But this powerful image, while compelling, might be an oversimplification that hides a deeper truth. What if the very concept of a beginning is something that itself requires an explanation? What if the initial conditions of the Big Bang, the precise settings that allowed for a universe with galaxies, planets, and conscious life, weren't random, but were actually dictated by the nature of the universe's own boundaries? This shifts our perspective from a single point of origin to a more holistic view where the edges of reality play a starring role in how time itself gets started. Think of it like this: the laws of physics are the rules of the game, but the boundary conditions are the setup of the playing field. They define the starting state. For our universe to have a consistent arrow of time, for entropy to be low at the beginning, allowing it to increase and create the flow we experience, the initial conditions had to be exquisitely specific. It's the ultimate example of fine-tuning. The question is, what could possibly account for that incredibly precise setup? One astonishing possibility is that the overall shape and structure of the entire cosmos, right out to its farthest edges, is what determined those initial conditions. If the universe is finite but unbounded, much like the surface of a sphere, then its global geometry itself acts as a boundary condition. There is no independent edge. The entire system is self-contained, and its geometry dictates how time can unfold from the initial moment. The beginning isn't just a point in time, it's an expression of the entire cosmos's shape. This idea becomes even more intriguing when we consider the multiverse hypothesis. In this vast cosmic landscape, our universe might be just one bubble in a frothing sea of universes, each with its own distinct physical laws and timeline. The edge of our universe in this scenario isn't an abstract mathematical concept but a very real interface, a boundary membrane separating our bubble from the wider multiverse. The properties of this boundary, the way it interacts with the inflating space beyond it, could have imprinted the specific low entropy state onto our newborn universe. Our arrow of time, the very reason we remember a past and not a future, might be a direct inheritance from the conditions at our cosmic frontier at the moment of our genesis. The edge isn't a later development, it was there, in a sense, at the very beginning, acting as a mold that shaped time's first breath. This perspective forces us to completely reconsider the Big Bang. It may not be the uncaused cause, but rather an event whose cause is tied to the larger structure of which it is a part. The origin of time is no longer isolated to a singularity, but is woven into the fabric of the cosmos's periphery. The edges are not afterthoughts or distant curiosities. They are foundational, playing an active and essential role in setting the stage for everything that follows, including the emergence of a timeline that allows for history, evolution, and us. Revisiting the Big Bang through this lens doesn't provide easy answers, but it opens up a far richer set of questions about where time truly comes from and how our entire cosmic story is connected from its very first moment to its farthest horizon. This radical notion that time might be a product of cosmic boundaries doesn't just reshape our scientific models. It sends tremors through the very foundations of philosophy, forcing us to reconsider ancient questions about infinity, eternity, and the nature of reality itself. For millennia, philosophers and theologians have grappled with the concept of a universe without beginning or end, an infinite and eternal existence. But if our experience of time is indeed generated at the edges, then a truly boundless cosmos, one with no edges whatsoever, would present a reality almost incomprehensible to us. It might be a realm without sequential order, a state of being where everything simply is all at once in a kind of timeless, eternal now. The flow of time we take for granted, the relentless march from past to future, could be a local phenomenon, a feature unique to a universe like ours that possesses a defined structure and boundary. This idea beautifully echoes some of humanity's oldest and most profound philosophical traditions. Many Eastern philosophies, like certain schools of Hindu and Buddhist thought, have long contemplated the cyclical nature of time and the universe, seeing our linear experience as a kind of grand illusion or Maya. In these views, time is not a fundamental truth but a construct that emerges from and is dependent upon the cyclical processes of creation and dissolution. Similarly, the concept that time is crafted at the edges resonates with the ancient Greek idea of the logos, an ordering principle that gives structure and reason to the cosmos. It suggests that time is not an independent absolute, but is instead woven into the fabric of the universe by its very architecture, its outermost frontiers acting as the loom. Perhaps the most unsettling philosophical question this raises for us, as conscious beings within this cosmic structure, is the question of free will. If the flow of time is not a neutral stage but is instead generated by specific conditions at the boundary of the universe, does that mean our entire timeline is, in a sense, predetermined? Are our choices, our triumphs, and our tragedies already encoded in the data on that distant cosmic horizon, merely playing out like a film projected from the edge? This touches on the age-old debate between determinism and free will, but with a cosmic twist. The boundary conditions could be seen as the ultimate initial settings, the cosmic firmware that dictates the laws of physics and the arrow of time within which all events, including our decisions, must unfold. Yet, this doesn't necessarily condemn us to a fatalistic existence. Think of it not as a pre-written script, but as the rules of a game and the shape of the playing field. The boundary conditions set the rules of physics. Gravity works this way. Entropy increases that way, but within those rules, an almost infinite number of plays can be made. Our free will might operate not by violating the laws of the cosmos, but by navigating the vast landscape of possibilities those laws allow. The edge creates the riverbed, but the water, the unfolding events of our lives, still finds its own unique path downstream. This perspective doesn't diminish our agency. It situates it within a magnificent cosmic context, connecting our most personal moments to the grand architecture of the universe. It makes the study of these distant frontiers not merely a scientific pursuit, but a deeply human one, a quest to understand the very framework that makes our existence and our experiences possible. While the concepts of edges generating time are profoundly philosophical and physical, they are not just speculative poetry. they are grounded in rigorous mathematical frameworks that allow us to test these incredible ideas with precision. To move from grand analogy to tangible theory, we must turn to the language of the cosmos itself, mathematics. It provides the tools to build models where time is not an input but an output, a consequence of the universe's shape and boundaries. One of the most powerful tools in this endeavor is something known as the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT for short. This is a concept that emerges from the world of string theory, and while its name sounds intimidating, its core idea is breathtakingly elegant. It proposes a perfect mathematical duality, a kind of cosmic dictionary between a volume of space that contains gravity and its lower dimensional boundary. In simpler terms, it suggests that a theory describing a gravitational universe like ours can be completely and exactly equivalent to a theory that lives on its boundary and has no gravity in it at all. This is the ultimate expression of the holographic principle, translated into precise equations. The dynamics of every star, every particle, and every moment of time unfolding within the bulk of that space are perfectly mirrored by the interactions of quantum fields dancing on its distant, lower dimensional edge. This isn't just a mathematical curiosity, it's a revolutionary way to understand how time could be generated. In this framework, the boundary is not a passive reflector but an active computer. The quantum field theory on the boundary is like the software processing information according to its own rules. The unfolding of time within the volume of space is the hardware running that program, the physical manifestation of that computation. The steady tick of time we experience could be the internal perception of this immense information processing happening at the cosmic horizon. The boundary conditions, the specific setup of the fields on that surface, effectively dictate the arrow of time and the laws of physics for the entire interior. This gives us a precise, calculable model where the edge is indeed the temporal architect, and the flow of chronology is an emergent story written in the data on the frontier. Beyond AD-S/CFT, other mathematical frameworks like conformal field theory allow physicists to explore how the symmetries and properties of a surface can dictate the behavior of a system. These tools provide a playground for testing what happens when you change the boundary conditions. What if the edge of the universe were reflective instead of absorbing? What if it had a different shape or a different set of fundamental rules encoded on it? By tweaking these mathematical parameters, researchers can run simulations in silico, observing how the emergent property of time within the model changes in response. It allows for a form of theoretical experimentation that would be impossible in the real cosmos, offering a glimpse into how different kinds of time, cyclic, static, or even multi-directional, could arise from different types of edges. This mathematical perspective is crucial because it transforms a mind-bending philosophical concept into a potentially testable scientific hypothesis. While we cannot yet travel to the edge of the universe to take measurements, we can use these abstract tools to make specific predictions about what signatures an edge-generated time would leave on the universe we can observe, such as specific patterns in the cosmic microwave background or correlations in the large-scale structure of the cosmos. The equations are the bridge from the unimaginable frontier to the observable present, providing a clearer picture of how our most familiar dimension might be the most profound cosmic echo. Of course, we cannot pack a spaceship and journey to the literal edge of the cosmos to take a snapshot of time being born. The very idea is, with our current understanding, a physical impossibility. Yet, the beauty of science is its power to infer profound truths from subtle clues, to listen to the faint echoes of the universe and decipher their meaning. And when it comes to the radical idea that boundaries create time, there are indeed intriguing echoes for us to hear. The evidence is indirect, but it is mounting, painting a picture that is far more than mere speculation. One of our most powerful windows into the infant universe is the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space. This ancient light, released when the universe was just 380,000 years old, is not perfectly uniform. It is etched with tiny, faint variations in temperature, hot and cold spots that form a specific pattern across the entire sky. Cosmologists have meticulously mapped this pattern, and it serves as a cosmic fingerprint, encoding the initial conditions and physical laws of our nascent reality. The critical question is, what imprinted that specific fingerprint? The patterns we see are consistent with the universe having undergone a period of rapid inflation, a concept we've discussed. But what set the rules for that inflation? The characteristics of these temperature fluctuations could very well be the observable consequence of the universe's primordial boundary conditions. The way space was stretched and quantum fluctuations were amplified during inflation processes that ultimately seeded all the galaxies we see today may have been dictated by the fundamental properties of the cosmos's own geometry and edges at that earliest moment. By studying the precise statistical properties of this radiation with increasingly sensitive instruments like the Planck satellite, we are essentially reading the user manual for our universe, a manual that might have been written at its outer limits. Here on Earth and in the space around it, we have managed to create laboratories that mimic the most extreme conditions where boundaries warp time. The most stunning confirmation comes from our study of black holes and their event horizons. While we can't visit one, we can observe their effects on their surroundings with incredible precision. For decades, the time dilation effects predicted by Einstein's theory of general relativity, that time slows down in a powerful gravitational field, have been confirmed. The Global Positioning System, or GPS, is a perfect everyday example. The satellites in orbit, experiencing slightly less gravity than us on Earth's surface, have clocks that run faster by a tiny but measurable amount. If engineers didn't constantly correct for this relativistic effect, your phone's navigation would be off by several miles within minutes. This is a direct, practical validation that gravity, and by extension the intense gravity at a boundary like an event horizon, directly governs the flow of time. Furthermore, the groundbreaking detection of gravitational waves by the LIGO and Virgo observatories has opened an entirely new sense for exploring these phenomena. These ripples in spacetime are caused by cataclysmic events like the merger of black holes. The signals we receive are a direct reading of how these immense objects warp space and time in their final moments before merging. By analyzing these waves, we are testing the very nature of gravity and horizons in regimes of power and violence that we could never recreate on Earth. Every chirp and ring-down signal from a black hole merger is a data point on how boundaries behave and interact, providing a powerful analog for understanding the principles that might be at work on the cosmological scale. The future of this exploration is even more thrilling. Next-generation gravitational wave detectors, like the Laser Interferometer Space Antenna, or LISA, planned for the 2030s, will be sensitive to lower frequency waves, allowing us to probe the mergers of supermassive black holes and potentially even echoes from the Big Bang itself. Meanwhile, powerful new telescopes, like the recently launched James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope, will peer deeper into the history of the universe than ever before, measuring the effects of dark energy and the rate of cosmic expansion with unprecedented accuracy. This data is crucial because it directly relates to the nature and behavior of our cosmological horizon. By precisely measuring how the expansion has changed over billions of years, we can better understand the properties of dark energy, the force that is shaping that ultimate boundary. Any deviation from our expected models could be a clue that something profound is happening at the edge, that the horizon is not just expanding but actively interacting with the fabric of space-time in a way that generates the temporal structure within. The path from philosophical speculation to testable science is a long and challenging one, but we are firmly on it. Each new dataset, each more precise measurement of the cosmic microwave background, each gravitational wave signal, and each deep field image from a space telescope is another piece of the puzzle. We are gathering the evidence that will allow us to ask the universe a direct question. Is time a fundamental stage, or is it a magnificent performance generated by the grandest stage of all, its own outer edge? The instruments we are building today are the tools that will finally let the cosmos answer. But our exploration of edges and time doesn't have to stop at the boundaries of our own cosmos. What if our universe is just one bubble in a vast, frothing cosmic foam? This is the heart of the multiverse hypothesis, an idea that pushes the concept of edges into an entirely new and dizzying dimension. If multiple universes exist, each with its own unique physics, then each one might also operate on its own distinct timeline. Some universes could have time that flows backward from our perspective, others might have time that loops in circles, and some could exist in a state of timeless equilibrium. In this breathtakingly vast landscape, the edges between these universes become the most fascinating frontiers of all. They are no longer just the outer limit of one reality. They are the interfaces where completely different realities meet. These boundaries between universes could be unimaginably dynamic regions where different laws of physics and different arrows of time interact, negotiate, and perhaps even influence one another. Consider the theory of eternal inflation, which suggests our universe began as a tiny bubble that rapidly expanded within a larger, hyper-inflating meta-universe. In this model, new bubble universes are constantly popping into existence, each with its own random set of physical constants. The boundary of our universe, in this view, is the membrane of our bubble, a wall separating our space-time from the inflating background. At this boundary, the radically different properties of the two realms meet. What happens to time at such an interface? It's possible that the very beginning of time within our bubble, the start of our arrow of time, was determined or influenced by the interaction at this membrane. The edge wasn't just a birthplace, it was a mixing zone where the temporal potential of the wider multiverse was filtered into the specific timeline we inherited. These boundaries could be where time is not just created but curated, with each universe receiving its own unique chronological signature. This multiversal perspective completely transforms the scale of our inquiry. Time creation is no longer a process isolated to a single cosmos. It becomes a vast, ongoing multiversal phenomenon. The edges between universes might facilitate a kind of temporal diversity, ensuring that not all realities experience existence in the same way. Some boundaries might be porous, allowing for subtle leaks of information or influence that could gently nudge the flow of time in adjacent universes. Others might be rigid and impenetrable, fiercely protecting the chronological integrity of each bubble. This creates a cosmic landscape of immense complexity, a tapestry of times woven together at the seams by these incredible interfacial boundaries. Our own experience of a linear, forward-moving time is suddenly demoted from a universal truth to a local custom, one possibility among a near infinity of others, all made possible by the nature of the edges that define each individual reality. This profound connection between the cosmic and the conscious invites us to reconsider the very nature of our moment-to-moment awareness. We all share this deep, intuitive feeling that time flows, a steady stream of nows moving from a fixed past into an open future. But neuroscience reveals that this feeling is a sophisticated construction, a narrative woven together by our brains from a chaotic storm of sensory inputs and electrical signals. Our perception of a continuous timeline is in fact a clever illusion, a story the brain tells itself to make sense of a world where events don't always arrive in a neat order. The brain must constantly synchronize signals that travel at different speeds. The sound of a clap reaches us milliseconds after the sight of the hands coming together, yet we perceive them as simultaneous. This intricate processing creates what we experience as the present moment, a roughly 3-second window that feels like now. If this entire neurological machinery is building our personal sense of time, could its fundamental operating system be tuned to the rhythm of the cosmos itself? The constants of our universe, the speed of light, the strength of gravity, the mass of an electron, are the unchanging rules that govern how everything interacts, from the smallest particle to the largest galaxy. These constants are not just numbers in an equation. They dictate the maximum speed at which any cause can lead to an effect, the rate at which neural impulses can fire, and the very chemistry that allows our brains to function. These constants are the universal drumbeat, and our consciousness is the dancer moving to its rhythm. If, as we've explored, these universal constants are themselves set or influenced by the boundary conditions at the edge of the universe, then a breathtaking chain of connection emerges. The way our brains stitch together a coherent flow of time, the very duration of our subjective present, might be an echo of a process happening on the farthest frontier of reality. Our internal clock is not just set by the sun rising and setting. It might be fundamentally calibrated by the primal settings of the cosmos, written into its architecture at the beginning and maintained at its edges. This idea bridges the vast chasm between the impossibly large and the intimately small, suggesting that the flow of time is not something that happens to us, but something that happens through us. We are not passive observers of a cosmic clock. We are active participants in its expression. Each moment of consciousness, each feeling of a second passing, could be a localized, personal manifestation of the universe's ongoing creation of time at its boundaries. It means that when you feel a moment of anticipation waiting for a loved one, or a sense of nostalgia listening to an old song, you are not just experiencing a private memory. You are tuning into the deepest rhythm of existence, a rhythm generated billions of light years away. Your personal temporality is a unique and precious reflection of cosmic activity, making each of us a living, breathing testament to the universe's most profound mystery. To truly grasp how the universe's farthest edges might weave the fabric of time, we don't necessarily need a starship. Sometimes the most profound cosmic insights begin right here on Earth, inside powerful computers and ingenious laboratory experiments. Scientists are increasingly turning to advanced simulations and analog systems to model these elusive edge effects, creating virtual universes and physical analogs that allow us to experiment with the nature of reality itself. Imagine programming a supercomputer with a specific set of rules for a boundary, perhaps defining it as a surface that absorbs information or one that reflects it back. By running a simulation of a virtual cosmos with these programmed edge conditions, researchers can watch, in accelerated detail, how the properties within that digital universe evolve. Does a stable arrow of time emerge from the chaos? Does the interior develop a clear past, present, and future based solely on the rules enforced at its outer shell? These computational experiments act as a cosmic testbed, a digital playground where we can tweak the parameters of existence and observe the consequences, offering a tangible way to explore how our own reality might be shaped by its frontiers. Beyond pure software, physicists also construct remarkable analog systems in the lab that mimic the behavior of exotic cosmic horizons. One fascinating example involves using a carefully controlled flow of water. Researchers can create a figurative waterfall so swift that the flowing water reaches a speed faster than the waves moving against the current, creating an effective horizon that waves cannot cross. This setup beautifully analogs the event horizon of a black hole, and scientists have used it to observe the analog of Hawking radiation, the very phenomenon where particles are generated at a boundary. By studying how these ripples and particles behave at this man-made horizon, we gain physical, observable insights into how real horizons can create something from nothing. These experiments don't just simulate, they physically demonstrate that boundaries are not inert, proving they can be sites of genuine generation and transformation, lending powerful credibility to the idea that the universe's edge could be performing a similar, grander feat with time. The true power of this technological approach lies in its flexibility to ask, what if questions that the real universe won't yet answer? What if the cosmic boundary isn't a one-way street but a two-way mirror, partially reflective? A simulation could show whether such an edge would lead to a universe where information echoes back, potentially creating complex temporal loops or even interfering with the clear, linear arrow of time we experience. What if the edge is dynamic and interactive, changing its properties based on the state of the universe within? This could model a cosmos that evolves its own laws of physics over time, with the boundary acting as an adaptive processor. By running countless variations, we move from a single philosophical idea to a rich spectrum of possibilities, each with testable predictions about the patterns we should see in the real cosmos. This method transforms an abstract, almost mystical concept into a rigorous field of study, where each simulation brings us closer to understanding the possible architectures of time and our place within a universe that might be computing its own existence at the very edge of everything. Our journey to understand the edges of the cosmos is not a new one. It is a story etched into the very heart of human history, reflecting our deepest fears, hopes, and intellectual revolutions. Long before telescopes and satellites, our ancestors gazed at the horizon and wondered what lay beyond. In ancient mythologies, the world often had a literal edge, a precipice where the known gave way to the terrifying and divine. The Norse spoke of Yggdrasil, the great world tree, whose roots and branches held the 9 realms together, implying a cosmic structure with limits and boundaries. Babylonian cosmology depicted the Earth as a flat disk floating in a vast sea, surrounded by a massive mountain wall that held up the dome of the heavens. These edges were not just physical barriers, they were psychological ones, separating the ordered world of human experience from the chaotic, timeless realm of gods and monsters. In these early conceptions, the edge was the absolute limit of safety and knowledge, a place where the very concept of time as humans understood it might break down into eternity or chaos. This mythological view began to crystallize into a more structured, though still Earth-centered, model with the ancient Greeks. Philosophers like Aristotle proposed a universe of nested crystalline spheres, with the Earth motionless at the center. Each planet, the Sun, and the Moon were embedded in their own transparent, rotating sphere, and the outermost sphere, the primum mobile or first mover, held the fixed stars. But what was beyond that final sphere for Aristotle? Nothing. It was the ultimate boundary of the universe, a perfect, immutable realm where change and time, as we know them, ceased to exist. This outermost sphere was the domain of the eternal and the divine, a place beyond decay and alteration. Here, the edge was not just a spatial limit, it was a temporal one. It marked the boundary between the imperfect, time-bound world of Earth and the perfect, timeless reality of the heavens. This idea profoundly influenced medieval European thought, blending with Christian theology to place the abode of God and the angels beyond the sphere of the fixed stars in a realm entirely outside of time. The edge was the gateway to eternity. The next great revolution came from a simple yet profound shift in perspective, placing the sun, not the Earth, at the center of the solar system. Copernicus, Kepler, and Galileo dismantled the cozy, finite universe of nested spheres and replaced it with a vast, sun-centered system. This was more than an astronomical correction. It was a philosophical earthquake. If the Earth was not the center, then the cosmic edges were not where we thought they were. The universe suddenly felt immeasurably larger, and the old boundaries began to dissolve into a void of unknown depth. This expansion of space forced a corresponding rethinking of time. If the universe was infinite, as thinkers like Giordano Bruno proposed, then did time also stretch to infinity in both directions? The edge was no longer a tangible sphere but a fading horizon of comprehension, and time became an endless river with no discernible source or mouth. The Newtonian universe that followed was an infinite, static stage, an absolute space and time that provided the backdrop for all events. The edges, in a sense, vanished into an endless void, and time became a universal, unchanging tick of a master clock, independent of the cosmos it measured. The 20th century brought the next seismic shift with Einstein's theories of relativity. Space and time were no longer separate and absolute. They were woven together into a single, dynamic fabric called space-time. This fabric could be warped and curved by mass and energy. The concept of an edge transformed once again. A finite universe no longer needed a physical boundary. It could be finite yet unbounded, like the surface of a sphere. If you traveled in one direction for long enough in a positively curved universe, you would eventually return to your starting point without ever hitting a wall. This geometrization of the cosmos changed the question from "what's on the other side of the edge" to "what is the overall shape of reality?" The Big Bang theory then gave this curved spacetime a beginning, a moment of genesis where time itself seemingly began. The edge was no longer a place in space but a point in time, a temporal singularity where the laws of physics broke down. Our focus shifted from looking for a wall at the end of the universe to peering back toward a moment of creation at the beginning of time. Today, we find ourselves in a fascinating position, armed with the tools of quantum mechanics and general relativity, revisiting these ancient questions with a modern twist. We are coming full circle, in a way, back to the idea that edges are dynamic and active, but now with a scientific rigor the ancients could never have imagined. The holographic principle and the study of black hole horizons have taught us that boundaries are not passive limits but sites of immense information processing and creative potential. We are beginning to see the cosmological horizon not as a barren endpoint, but as a vibrant interface that might actively generate the laws of physics and the flow of time within the universe. This modern view synthesizes the historical journey. It acknowledges the intuitive human need for a boundary, incorporates the relativistic understanding of a dynamic spacetime, and uses quantum theory to propose that the edge is where the most fundamental processes occur. Our understanding has evolved from a flat Earth's cliff to a divine sphere, from an infinite void to a curved geometry, and now to a computational horizon. Each era's view of the edge directly shaped its understanding of time, and today's cutting-edge theories suggest that this relationship is more profound than ever. The edge doesn't just contain time. It conjures it into being, fulfilling an age-old human intuition that the boundaries of reality are where the deepest mysteries reside. Standing on the precipice of this new understanding, we are not merely passive observers of the cosmos. We are active participants in a grand investigation, armed with an ever-growing arsenal of technological marvels designed to probe the deepest mysteries of existence. The question of whether the universe's edges are actively weaving the fabric of time is no longer confined to the realm of pure philosophy or abstract mathematics. It is steadily becoming a testable scientific hypothesis, thanks to a new generation of tools that will extend our senses to the very limits of reality. The future of cosmic exploration is poised to turn these mind-bending ideas into measurable data, and the instruments leading this charge are nothing short of breathtaking. Consider the upcoming Nancy Grace Roman Space Telescope, slated for launch later this decade. While its predecessor, the James Webb Space Telescope, peers back at the first galaxies, Roman is specifically designed to tackle the mystery of dark energy with unprecedented precision. By mapping the distribution of millions of galaxies and measuring the distances to thousands of supernovae across immense cosmic time, it will provide the most detailed chart yet of the universe's expansion history. This data is absolutely crucial because it directly measures the behavior of our cosmological horizon, the very edge that might be generating time. Any subtle deviation from our expected models of how dark energy behaves could be the first tangible clue that this horizon is not a passive byproduct of expansion, but an active, dynamic interface with profound influence over the temporal structure within. It's like taking the pulse of the universe's boundary from billions of light years away. On an even more ambitious scale, the Laser Interferometer Space Antenna, or LISA, represents a monumental leap in our ability to listen to the cosmos. This planned space-based observatory, consisting of 3 spacecraft flying in a giant triangular formation, will detect gravitational waves at frequencies too low for Earth-based instruments to hear. This will open an entirely new window onto the universe, allowing us to hear the mergers of supermassive black holes, the very objects whose event horizons have taught us so much about how boundaries warp time. But even more profoundly, LISA might be sensitive enough to detect a faint background hum of gravitational waves left over from the Big Bang itself. This primordial rumble would carry encoded information about the universe's birth and its very first moments, potentially revealing the initial conditions that were set, perhaps, by its primordial boundaries. It would be like finding the original user manual for spacetime. Meanwhile, here on Earth, the pursuit continues in massive underground laboratories and immense particle colliders. Experiments designed to directly detect dark matter particles or to probe the quantum nature of gravity at the smallest scales are all part of this interconnected quest. While they may not look at the cosmic horizon directly, they are investigating the fundamental ingredients and laws that govern the entire universe. Understanding the true nature of dark energy or achieving a successful theory of quantum gravity would provide the essential framework for interpreting the data from our telescopes and wave detectors. It would tell us what we should be looking for at the edge and how to recognize its signature. This interdisciplinary synergy where cosmologists, particle physicists, and theoreticians collaborate is where the most unexpected and revolutionary insights are likely to emerge, connecting the behavior of the smallest quanta to the largest cosmic structures. Of course, the most futuristic and speculative ideas involve not just observing, but someday directly probing these frontiers. While the concept of sending a physical probe to the cosmological horizon remains firmly in the realm of science fiction due to the unimaginable distances and energies involved, it sparks the imagination. Perhaps a sufficiently advanced civilization could develop quantum sensors or utilize entangled particles to gather information from those distant reaches indirectly. The very act of contemplating such possibilities pushes the boundaries of engineering and physics, forcing us to think creatively about how to test the seemingly untestable. This ongoing exploration, fueled by both rigorous science and bold speculation, promises to utterly transform our understanding of reality. We are moving from wondering if the edge creates time to designing experiments that could one day tell us how. This journey into the unknown, driven by insatiable curiosity, ensures that our cosmic story is still being written, with its most astonishing chapters yet to come. This perspective that time might be a cosmic emission from the farthest frontiers doesn't just rearrange our scientific models, it fundamentally reorients our sense of self and our understanding of purpose within an almost impossibly vast reality. If the steady flow of moments we experience is not a universal given but is instead generated by processes at the edge of the observable universe, it implies that our existence here and now is intimately, inextricably intertwined with the most distant architecture of the cosmos. This connection isn't merely poetic, it's physical, a literal tether of causality binding our conscious present to the dynamic activity of the cosmological horizon. This realization invites a profound and humbling awe, a sense that we are not isolated observers in a cold, empty void but active participants in a grand, dynamic system whose workings span the entirety of space and time. Our most personal experience, the feeling of a second passing, is a local whisper of a phenomenon happening on the most colossal scale imaginable. This interconnected view naturally extends into the ethical realm, potentially reshaping how we approach our responsibilities both on Earth and beyond. If our timeline is a gift generated and maintained by the stable, large-scale structure of the universe, it underscores the incredible rarity and fragility of the conditions that allow for conscious experience. This could foster a renewed ethical imperative for planetary stewardship, a recognition that preserving the delicate balance of our local environment is not just a practical concern but a moral one, honoring the cosmic circumstances that made our existence possible in the first place. Furthermore, as we contemplate venturing beyond our planet, this framework encourages a philosophy of space exploration rooted in reverence rather than mere resource extraction. Approaching other worlds with the understanding that they too are part of this immense, time-generating system could inspire a more holistic and respectful ethos, one that sees exploration as a way to learn from the cosmos rather than to conquer it. On an existential level, this idea challenges our deepest fears about mortality and the longing for legacy. We often measure our lives against the relentless march of time, fearing that our brief moment will be forgotten in the vastness of eternity. But if time itself is a contingent property of our specific cosmic structure, it reframes that very vastness. The eternity we fear is not a pre-existing emptiness waiting to swallow us. It might not exist at all outside the context of a universe with edges like ours. Our lives are not small because the universe is large. Our lives are a unique expression of the universe's creativity, a localized flowering of the same process that spins time from the void at its horizon. This doesn't promise immortality, but it offers a different kind of solace. Our consciousness, our stories, and our brief flash of experience are not insignificant. They are a valid and valuable part of the universe's own story, a story that includes the creation of time itself. Our search for meaning is not a futile struggle against an indifferent cosmos. It is the cosmos becoming aware of itself, using us to reflect upon the magnificent and mysterious process of its own unfolding. Of course, the scientific journey is never a straight line from question to answer. and this radical idea that the universe's edges are weaving time is no exception. It's a hypothesis that sparks fierce debate and healthy skepticism within the physics community, and for good reason. Many respected physicists maintain a very different view, that time is not an emergent property cooked up at the boundaries, but is instead a fundamental, irreducible ingredient of reality, as basic as space itself. In this more traditional framework, the flow of time isn't something that needs to be generated. It's the foundational stage upon which all other events play out. From this perspective, any boundaries or edges we talk about, including our cosmological horizon, are themselves emergent phenomena. They are consequences of how the universe has evolved within this pre-existing spacetime arena, not the cause of it. This isn't a fringe view, it's a cornerstone of how many interpret the equations of quantum mechanics and general relativity without adding extra layers of emergence. The debate often centers on a simple but crucial question: where should we place our Occam's razor? Proponents of fundamental time argue that inventing a complex process where time emerges from a timeless boundary adds unnecessary layers to our models. They point out that our most successful theories, from Newtonian mechanics to quantum field theory, all take time as a given input, a parameter that flows independently. Introducing the holographic principle or other edge-based mechanisms, they caution, might be solving a problem that doesn't exist or creating a more complicated solution than the mystery warrants. The burden of proof, they rightly insist, lies with those proposing the new, more complex idea, and that evidence, as we've discussed, is still largely indirect and inferential. This leads to the most common and perhaps most valid criticism: the stark lack of direct, observable evidence. A scientist might rightly ask, what specific, testable prediction does the time from edges theory make that the fundamental time theory does not? If both models can explain the cosmic microwave background and the arrow of time equally well, how do we decide between them? Critics argue that until we can make a prediction that is uniquely borne out by experiment, the idea remains in the realm of compelling speculation, a beautiful and mathematically intriguing story, but not yet a confirmed chapter in the textbook of physics. This cautious approach is not a lack of imagination. It is the essential rigor that prevents science from drifting into pure philosophy. It demands that we stay tethered to what we can observe and measure, even as we let our minds wander to the farthest edges of thought. Yet, it is precisely this tension between bold speculation and rigorous skepticism that drives science forward. These debates are not signs of weakness or confusion in cosmology. They are the engines of discovery. The conflict between Einstein's relativity and quantum mechanics, for instance, has fueled a century of progress, giving us everything from semiconductors to the quest for a theory of everything. In the same way, the debate over the nature of time pushes both sides to refine their arguments, sharpen their models, and seek ever more creative ways to test the untestable. It forces those who believe time is emergent to dig deeper for concrete evidence, and it challenges those who believe it is fundamental to explain why the universe appears to have such a specific, low entropy starting point. This dynamic process of challenge and refinement is how science self-corrects, how it inches closer to a truer understanding of reality, even if that path is messy and filled with disagreement. By engaging with these controversies, we don't weaken the story. We show it in its true light, a living, breathing, and thrillingly uncertain human endeavor to solve the greatest mysteries of all. While the idea that time might be woven into existence at the farthest edges of the cosmos sounds like the plot of a science fiction novel, its echoes resonate in surprisingly practical ways, touching technology we use every day and shaping the future we are building. Consider the device in your pocket or car that tells you exactly where you are on the planet. The global positioning system is a modern marvel, but it would be utterly useless without a deep understanding of how gravity warps time. Each satellite in the GPS constellation contains an incredibly precise atomic clock. According to Einstein's theory of general relativity, time runs faster for objects in a weaker gravitational field. Because these satellites are farther from Earth's mass than we are, their clocks tick at a slightly different rate than clocks on the surface. Furthermore, their high orbital speed introduces a special relativistic effect that slows time down. The net result is that if these tiny, predictable time distortions were not meticulously calculated and corrected for, the entire system would accumulate errors of several miles within a single day, rendering turn-by-turn navigation comically inaccurate. This isn't a minor technicality. It is a daily, practical validation that gravity dictates the flow of time. It proves that the structure of spacetime is not a static stage but a dynamic fabric, and our ability to navigate depends on understanding its wrinkles, a principle that becomes exponentially more critical the farther we travel from home. This profound connection between time and the structure of reality is also seeding a revolution in how we think about computing itself. Traditional computers operate on a classic binary framework of ones and zeros, processing information in a linear, step-by-step sequence. But if time is not a fundamental feature but an emergent property, it opens the door to radically different computational models. Scientists are now exploring the potential of emergent time computing, inspired by theories like the holographic principle. Imagine a computer that doesn't process information in a strict chronological sequence, but rather by simulating the complex, interconnected relationships of a network, from which a coherent sequence of events emerges naturally. This could lead to processors that handle certain problems with unimaginable efficiency, tackling complex simulations of quantum systems or cosmological models in ways our current machines can scarcely dream of. The very concept of a clock speed could be redefined, not as a master timer dictating operations, but as a global property that arises from the system's internal dynamics. This isn't just about building faster laptops. It's about pioneering a new form of information processing that mirrors what we suspect might be happening at the universe's own horizon, turning the cosmos into the ultimate blueprint for the next technological leap. On a more personal level, this cosmic perspective can profoundly reshape our philosophy of daily life and our relationship with the moments we are given. Modern life often feels like a frantic race against the clock, a relentless pursuit of productivity that can leave us feeling drained and disconnected. But understanding time not as a cruel taskmaster, but as a fragile, emergent gift from the farthest reaches of the universe, can reframe our entire experience of it. If the steady flow of now is not a guarantee but a glorious cosmic accident, dependent on the specific architecture of our universe, then each second becomes infinitely more precious. This isn't about squeezing more activity into every hour. It's about cultivating a deeper appreciation for the mere fact that we are here to experience time at all. It encourages mindfulness not as a self-help trend, but as a form of cosmic gratitude, a recognition that our conscious awareness is riding a wave that began at the edge of reality itself. This shift in perspective can transform time management from a stressful exercise in optimization into a more meaningful curation of how we choose to inhabit each emerging moment, fostering a greater sense of presence and wonder in our everyday routines. This newfound appreciation for the cosmic nature of time also has a direct impact on the most ambitious human endeavor, our journey to the stars. As we set our sights on prolonged missions to Mars and beyond, the challenges of navigation and communication will become astronomically more complex. The simple radio signals we use to communicate with rovers on Mars already take minutes to travel one way, creating a significant lag. For travel beyond our solar system, this problem becomes insurmountable with current technology. However, a deeper understanding of spacetime itself, informed by theories about cosmic horizons and gravitational fields, could lead to breakthroughs. While the dream of warp drives remains speculative, researching the fundamental relationship between mass, energy, and the geometry of spacetime is the only path toward potentially revolutionary propulsion or navigation systems. Future spacecraft might not navigate by mapping stars alone, but by reading the subtle curvature of spacetime itself, using our knowledge of cosmic boundaries as a guide. In this future, an astronaut's most vital instrument might not be a telescope, but a supremely sensitive quantum gravimeter, charting a course through the invisible topography of the universe, a topography whose contours are intimately tied to the very generation of time. This demonstrates that the most abstract cosmic ideas are not intellectual luxuries. They are the essential groundwork for the next chapter of human exploration, turning philosophical curiosity into practical survival skills for a species destined to reach beyond its cradle. But this fascinating idea doesn't exist in a vacuum. It's deeply intertwined with some of the greatest unsolved puzzles in all of cosmology. Take dark matter, for instance, that mysterious, invisible substance that makes up about 85% of the matter in the universe. We can't see it, but we know it's there because of its powerful gravitational pull, which sculpts the vast cosmic web of galaxies and dictates how the universe expands. Now, if the edges of the cosmos are indeed active creators of time, then dark matter must play a crucial role in that process. Its gravitational influence is the primary architect of the universe's large-scale structure, meaning it directly shapes where and how those cosmic boundaries form. Think of dark matter as the unseen framework, the scaffolding upon which the visible universe is built. If this invisible scaffolding is concentrated or arranged in specific ways near the cosmological horizon, it could dramatically alter the conditions there. The immense gravitational pull of dark matter clusters at the edge could warp spacetime even more severely, potentially intensifying or modifying the very mechanisms we suspect are generating time's flow. It's a compelling feedback loop. Dark matter shapes the edge, and the edge, in turn, uses that structure to generate the temporal reality within which dark matter continues to evolve. This connection pushes us to consider an even more radical possibility. That dark matter isn't just a passive ingredient, but might be an active participant in the mechanics of time itself. Some speculative theories propose that dark matter could interact with itself through forces we don't yet understand, forces that operate only at the most extreme densities found near cosmic boundaries. These unique interactions at the frontier could be a key part of the engine that drives the universe's chronological order. Furthermore, the nature of dark matter is inextricably linked to the ultimate fate of the cosmos. The amount and behavior of dark matter directly influence whether the universe will expand forever, eventually contract in a big crunch, or rip itself apart. Each of these destinies presents a very different outcome for time. A big crunch, a collapse back into a singularity, could represent the absolute end of time, a final moment where the edge closes in and the process of time generation ceases. An eternal expansion driven by dark energy suggests time could flow on forever, but in a universe growing increasingly cold and dark, where the meaning of a moment becomes stretched into meaninglessness. Understanding how edges create time is therefore useless without also understanding what dark matter is and how it guides the universe toward one of these profound futures. The puzzle deepens when we bring other enigmatic players into the mix, like the true nature of singularities. At the heart of a black hole and at the moment of the Big Bang, our current laws of physics break down. General relativity predicts a point of infinite density and zero volume, a singularity. But most physicists believe this is a sign that our theory is incomplete, not that infinity actually exists. A theory of quantum gravity is needed to explain what truly happens at these extremes. If we are to believe that the universe's edges are creating time, then we must also ask, what happens at the ultimate edge, the singularity? Is it a true boundary where time ceases, or is it a gateway to something else? Some theories, like loop quantum gravity, suggest that the Big Bang wasn't a singularity but a big bounce, a transition from a previous universe that contracted. In this view, the edge isn't an absolute beginning but a transformational interface, and time could be cyclical, generated anew with each bounce. This directly connects the mystery of singularities to the mystery of time's origin, suggesting that the creative processes at the cosmological horizon we see today might be a faint echo of a much more violent and fundamental transformation that happened at the beginning. By weaving these threads together, dark matter, singularities, and the fate of the universe, we start to see a magnificent, interconnected tapestry of cosmology. No single mystery can be solved in isolation. The question of what time is cannot be divorced from the question of what dark matter is, which cannot be divorced from the question of how the universe will end. This integrative view is the true heart of modern scientific exploration. It moves us away from looking for a single theory of everything in a simplistic sense and toward a richer, more complex understanding where everything really is connected to everything else. The edge of the universe isn't some distant, irrelevant curiosity. It's the central hub where these fundamental forces and mysteries converge, interact, and ultimately define the reality we experience. This perspective doesn't just satisfy our curiosity, it provides a powerful roadmap for discovery, showing that a breakthrough in one area, like finally detecting and identifying a dark matter particle, could send shockwaves through every other field, potentially unlocking the secrets of time itself and revealing our true place in the grand cosmic scheme. When we think of gravity, we often picture the simple pull that keeps our feet on the ground, but Einstein's theory of general relativity revealed it to be something far more profound, a fundamental warping of the very stage upon which reality plays out. This stage is not a static grid of space with time ticking separately alongside it. It is a dynamic, interwoven fabric called space-time, and mass and energy are what bend and curve it. A massive object like a star doesn't just exert an invisible force, it creates a depression in this cosmic fabric, and this curvature is what we experience as gravity. This was Einstein's monumental legacy, a shift from force to geometry that forever changed our understanding of the cosmos. But perhaps its most astonishing implication is that this warping affects not just the paths of planets and light, but time itself. The stronger the gravity, the more time slows down, a phenomenon known as gravitational time dilation. This isn't a theoretical curiosity. It's a measured, everyday reality that keeps our satellite navigation systems accurate. But to grasp how gravity at the universe's edges might be creating time, we must first appreciate how it masterfully intertwines space and time into a single, malleable entity. Now take this incredible principle and push it to the absolute extreme. The most dramatic warping of space-time occurs where gravity is most intense, at the boundaries around immensely massive objects. A black hole's event horizon is the ultimate example, a point of no return where gravity is so powerful that it warps space-time into a closed surface. But what if the entire universe has a kind of horizon, a cosmological boundary defined by the overall gravitational field and the accelerating expansion driven by dark energy. At this farthest frontier, the collective gravity of all the matter and energy in the cosmos, combined with the strange repulsive force of dark energy, could be creating conditions of unimaginable curvature. Einstein's field equations, the mathematical heart of general relativity, are perfectly capable of describing universes with edges and boundaries. In fact, certain solutions to these equations explicitly include boundary terms that contribute to the overall dynamics of the cosmos. This means that the gravitational properties at the edge are not an afterthought. They are an integral part of the universe's structure, potentially dictating how time itself behaves and flows within the interior. The edge isn't just a place where space might end. It's where gravity's influence could be setting the very rules for chronology. This gravitational influence at the boundary might express itself through ripples in space-time itself, gravitational waves. These are not waves in space, they are literal vibrations of space and time, stretching and compressing the fabric of reality as they travel at the speed of light. They are generated by the most violent cosmic events, like the mergers of black holes and neutron stars. When we detect these waves with observatories like LIGO and Virgo, we are literally listening to the sound of space-time ringing. Now, imagine the universe's edge not as a silent wall, but as a continuous source of such gravitational activity. The immense energies and densities there could be generating a constant, faint hum of gravitational waves, a background resonance that permeates all of reality. This perpetual vibration could be constantly impressing a rhythm onto the cosmos, a fundamental frequency that helps to establish the consistent, uniform flow of time we experience. In this view, the arrow of time isn't just a thermodynamic phenomenon. It is a gravitational one, its direction and steadiness maintained by the endless hum emanating from the gravitational dynamics at the cosmic horizon. What's truly remarkable is how this modern exploration is a direct continuation of Einstein's own work, a testament to the enduring power of his ideas. He formulated general relativity over a century ago, based on profound thought experiments about falling elevators and the equivalence of gravity and acceleration. Yet, buried within the elegant tensor calculus of his equations were the seeds of these incredible modern concepts: black holes, gravitational waves, and an expanding universe with possible boundaries. He was famously uncomfortable with some of the stranger implications, like black holes and the cosmological constant. Yet his mathematics proved to be more visionary than he could have imagined. Today's physicists aren't overthrowing Einstein. They are using his own tools to push into realms he might have found unbelievable. They are taking his equations and applying them to the entire cosmos, asking what the solutions tell us about the global structure of space-time and how the conditions at its edge dictate the physics within. This is how science progresses, not by discarding the old but by building upon it, using the solid foundation of classical physics to reach for the most cutting-edge and revolutionary ideas about the nature of reality. This deep connection suggests that gravity is far more than just one of the four fundamental forces. It could be the master architect of temporal experience. While other forces govern interactions between particles, gravity governs the geometry of the arena itself. It is the director of the cosmic play, not just a player on the stage. At the universe's edge, where its influence might be most pure and unadulterated by local matter, gravity could be performing its most essential function, structuring the flow of time from the outside in. This perspective beautifully unites the physics of the very large with the human experience of the very small. The gravitational curvature at the cosmological horizon, light years away, could be the ultimate reason why cause precedes effect in your kitchen, why memories are stable, and why you experience a continuous and ordered present moment. Einstein's legacy, therefore, is not just a theory of gravity. It is the key that is helping us unlock the possibility that time itself is a gravitational phenomenon, born from the intense interaction between matter, energy, and the shape of the universe at its farthest frontier. To truly appreciate the profound weirdness of quantum entanglement, let's start not in the vastness of space, but in a laboratory here on Earth. Imagine a single particle that decays, splitting into two smaller particles that fly off in opposite directions. According to the strange rules of quantum mechanics, these two particles are now entangled. Their properties, like their spin or polarization, are not fixed independently but exist in a shared, fuzzy state of potentiality. It's only when we measure one of them that its property snaps into a definite value, and here's the utterly bizarre part: the other particle, no matter how far away it has traveled, instantly assumes the corresponding value. This connection seems to happen faster than light, a phenomenon that so disturbed Einstein he famously called it spooky action at a distance. It challenges our most basic classical intuition that objects need to be close together to influence one another, a principle known as locality. Entanglement suggests that the universe possesses a deeper, hidden layer of connectedness that operates outside our everyday understanding of space and time. Now let's take this spooky, non-local phenomenon and project it onto the largest canvas imaginable, the edge of the entire cosmos. If two particles can be entangled across a lab bench, could the entire interior of our universe be entangled with its own boundary? This is not just a wild speculation. It's a serious proposal emerging from the holographic principle and the AD/CFT correspondence we discussed earlier. The mathematics suggests that the quantum fields describing the particles and forces within the volume of the universe could be perfectly mirrored by and entangled with a web of quantum information residing on the lower dimensional boundary at the cosmological horizon. In this breathtaking view, the universe isn't just in a space with an edge. It is correlated with that edge in the most intimate way possible. Your existence here and now is not isolated. It is quantum mechanically linked to the farthest reaches of reality. This changes everything about how we might think about the emergence of time. If the interior and the boundary are entangled, then the flow of time we experience internally might not be a local phenomenon at all. It could be a direct consequence of this non-local correlation, the steady, reliable tick of time that allows for cause and effect within our universe could be the macroscopic result of countless entangled connections being constantly updated and resolved across the vast gulf between here and the horizon. It's as if the entire cosmos is performing a continuous, instantaneous dance, with every particle inside moving in lockstep with the data on the boundary. The arrow of time in this picture isn't driven by a local increase in entropy alone. It's propelled by the need to maintain this cosmic correlation, to keep the interior state consistent with the boundary state. Time becomes a story of maintaining a universal relationship. This perspective forces us to redefine what we even mean by an edge. It's no longer just a spatial limit, a place where space ends. It becomes a relational interface. The edge is defined not by a physical wall, but by this profound quantum connection. It is the other half of a cosmic partnership, a surface that is in constant, instantaneous communication with everything within. This relational view helps resolve a deep puzzle about non-locality and relativity. While entanglement seems to imply instantaneous influence, which would violate relativity's cosmic speed limit, the correlation itself doesn't actually transmit usable information or energy. You can't use entanglement to send a message faster than light. but you can use it to establish a universal correlation that defines the very structure of reality, including its temporal order. The edge, therefore, is not a distant, silent wall we are expanding toward. It is an active participant in a here and now relationship that defines the fabric of our existence, weaving the temporal tapestry of the entire cosmos through a web of spooky, instantaneous connections that make a mockery of mere distance. This mind-bending connection between the cosmic and the conscious brings us to a profound and often controversial idea known as the Anthropic principle. In its simplest form, the Anthropic principle observes a curious fact. The fundamental constants of our universe appear to be exquisitely fine-tuned for the existence of life. The strength of gravity, the mass of an electron, the precise energy state of the carbon atom. If any of these were even slightly different, stars wouldn't shine, planets wouldn't form, and complex chemistry, the basis for life as we know it, would be utterly impossible. We find ourselves in a universe that seems suspiciously well-suited for our own existence. The principle suggests we shouldn't be entirely surprised by this. After all, if the universe weren't this way, we wouldn't be here to notice. It's a statement about selection bias on a cosmic scale. Our very presence as observers filters the kind of universe we can possibly find ourselves in. Now apply this logic to our experience of time. We perceive time as a linear, one-way flow from past to future, a stable, reliable arrow that allows for memory, cause and effect, and the very process of biological evolution. But what if this isn't the only way time could be? What if other potential universes with different boundary conditions at their edges could have time that loops back on itself, fluctuates randomly, or doesn't exist in any meaningful sense at all? The Anthropic principle offers a startling possibility. Perhaps we experience time in this specific, linear way because it is the only kind of time compatible with the existence of complex, conscious observers like us. A universe without a clear and stable arrow of time would be a chaotic soup where causes don't reliably lead to effects, where molecules couldn't form the intricate structures needed for life, and where evolution could never get a foothold. In such a cosmos, no one would ever be around to wonder about the nature of time. This directly connects the grand architecture of the cosmos to our most personal, intimate experience. If the universe's edges are indeed the engines of time, then the specific properties of our cosmic boundary are not arbitrary. They are the precise settings that wound up the cosmic spring, creating the low entropy initial conditions that launched the arrow of time on its irreversible journey. Those boundary conditions had to be just right to produce a universe with a long, stable, and complex history. A history long enough for galaxies to coalesce, for generations of stars to forge heavy elements in their cores, for planets to form, and for life to slowly evolve over billions of years. Our perception of a flowing, linear time isn't a passive observation of a universal given. It is an active, necessary consequence of living in a universe whose edges are tuned for the possibility of our existence. This idea transforms our place in the cosmos from a happy accident to an integral part of the cosmic story. It's not that the universe was designed for us, but rather that we are a natural product of a universe with a particular kind of structure. The way we experience moments, the feeling of a past that is fixed and a future that is open, is deeply woven into the fabric of reality by the conditions at its farthest frontier. This adds a deeply philosophical and personal dimension to the science. It means that your morning coffee cooling on the counter, your memory of a childhood birthday, your anticipation for an event next week, all these personal experiences are not separate from the cosmos. They are local, conscious expressions of the universe's global architecture. The steady march of time you feel is the universe at its most fundamental level, expressing a property that allows it to become aware of itself. This perspective doesn't just answer a scientific question, it invites a sense of profound connection, suggesting that in wondering about time, we are truly the universe beginning to understand its own nature. Long before telescopes and equations, humanity told stories to make sense of the cosmos, and in these ancient narratives, we find a profound and recurring theme. The edge of the world is not a barren end, but a place of immense power and transformation, a threshold where time itself is negotiated. Consider the ancient Egyptian vision of the universe where the sky was the goddess Nut, her body arched over the earth, touching the horizon with her fingertips and toes. Each evening she would swallow the sun god Ra, who would journey through her star-studded body through the night, only to be reborn from her womb at dawn. The horizon was not a limit, it was a creative, cyclical portal where day and night, life and death were perpetually regenerated. This wasn't mere fantasy, it was a cosmological model that located the engine of time's rhythm at the boundary between the earthly and the divine. This intuition that the periphery holds creative power echoes across countless cultures. In Norse mythology, the great world tree Yggdrasil connected the 9 realms, its roots and branches stretching into the unknown. The well of fate, Urðarbrunna, lay beneath one root where the Norns wove the destinies of gods and humans. The edge here was not a spatial wall but a temporal wellspring, the source from which the tapestry of past, present, and future unfolded. Similarly, many indigenous cultures across the Americas envision this world as a middle place, sandwiched between an upper world and an underworld, with sacred sites like mountains or caves serving as conduits between these realms. These points of contact were where shamans could journey to retrieve knowledge, heal the sick, or influence events. They were interfaces where the flow of time and causality could be actively interacted with, not just passively observed. These myths reveal a deep-seated human understanding that boundaries are not inert. They are dynamic membranes. The edge of the flat earth in ancient tales wasn't just where you might fall off. It was where the mundane rules of the known world gave way to the fantastic and the primordial. It was where monsters might dwell, where gods resided, or where one might find the fountain of youth, a place where the normal flow of time could be altered, reversed, or escaped entirely. This portrayal of edges as transformative zones is a stunning pre-scientific echo of the modern theories we've been exploring. The event horizon of a black hole, where time appears to stop and the laws of physics break down, is the scientific equivalent of the mythological abyss. The cosmological horizon from which our arrow of time may be projected is the modern incarnation of the sacred mountain peak that touches the heavens. This cultural lens does more than just provide interesting parallels. It enriches the scientific discussion by revealing that the quest to understand time's origin at the boundaries is not a new, coldly rational endeavor. It is the latest chapter in an ancient, fundamentally human inquiry. Our ancestors, looking out at the literal horizon, understood instinctively that the limits of their perception were also the sources of great mystery and power. They used the language of story and symbol to express what we now strive to capture with mathematics and physics, that reality is shaped at its frontiers. This continuity bridges the supposed gap between art and science, showing them to be complementary ways of exploring the same profound mystery. The physicist calculating the entropy gradient at the cosmic horizon and the shaman journeying to the edge of the world are, in a deep sense, engaged in the same quest to understand how the order of our experienced world emerges from the creative chaos at its periphery. Our modern scientific theories, in their own way, are our culture's mythology, a grand, evidence-based story about where we come from and how the world works. And it is a story that, like all the great myths before it, points to the edge as the place where it all begins. But this journey into the idea that time might be an emergent property crafted by the universe's boundaries forces us to confront an even more radical and unsettling possibility. What if time isn't just something that emerges from a deeper level of reality? What if it isn't real at all? This is not a new question, but one that has haunted both physicists and philosophers for centuries, and it gains incredible momentum from the notion of edge-generated chronology. If the flow of time is a product of specific cosmic conditions at the horizon, then it ceases to be a fundamental feature of existence and starts to look more like a compelling, persistent illusion, a story the universe tells itself, with us as the characters who have come to believe it completely. Think about the experience of watching a movie. The story unfolds on the screen with a clear beginning, middle, and end. We feel suspense, anticipation, and resolution as the plot moves forward. But if you were to examine the film reel itself, you would find all those moments existing simultaneously, frozen as individual frames. The flow, the narrative, the sense of time passing. It's all a projection, an emergent property of light passing through the sequence of frames. Now apply that analogy to the cosmos. The holographic principle suggests that our entire 4D universe, with its rich history and future, is encoded on a 2D boundary. In that description, every moment, the Big Bang, the death of the sun, you reading this sentence right now, exists all at once on that cosmic film reel. The feeling of a flowing now is our subjective experience of the projector's beam moving through those frames. The edge isn't just creating time, it's storing the entire timeline, and our consciousness is providing the illusion of motion. This perspective finds a powerful ally in the equations of general relativity. Einstein's theory beautifully unifies space and time into a single, four-dimensional block universe. In this model, the past, present, and future are not successive states. They are all equally real and exist eternally within this static block. Your birth, your life, and everything that will ever happen to you are all fixed points in this vast, unchanging structure. The feeling that time is passing, that the future is open and the past is fixed, is, according to this view, a complete illusion generated by the peculiar way our brains process information. We are like ants walking across a painted mural, experiencing each detail sequentially and mistaking that journey for the creation of the painting itself. The theory of edge-generated time fits perfectly into this block universe idea. The cosmic boundary is the frame that holds the entire mural, and the laws of physics are the paint that defines every fixed detail within it. This challenges our most basic, visceral experience of reality. How do we reconcile the undeniable feeling of a flowing present with the possibility that it's a cognitive trick? Neuroscience offers some clues. Our brain is not a passive recorder of time. It's an active constructor of it. It takes a chaotic stream of sensory input, sights, sounds, touches, and stitches them together into a coherent narrative, creating a smoothed-out experience of the present moment. This process involves memory, anticipation, and a constant updating of our mental model of the world. The now you feel is actually a slightly delayed reconstruction of events that have already happened, a best-guess narrative your brain assembles to help you navigate the world. So, not only might time be an emergent property of the cosmos, but our perception of it is an emergent property of our neurology. We are experiencing a useful fiction built on top of a deeper fiction. So, does this mean time is utterly meaningless? Not at all. Even if it is an illusion, it is an incredibly robust and necessary one. For us, and for the universe as we interact with it, time is as real as it gets. Causality, memory, aging, the very process of thought, all require this stable arrow of time to function. The illusion has rules and structure, and those rules are what allow for complexity, life, and consciousness to arise. The debate isn't about whether we should ignore time, but about understanding its true nature. Is it a primary, fundamental dimension, or is it a secondary, derivative property that emerges from a timeless, deeper reality? The concept that time is generated at the edges powerfully supports the latter view. It suggests that the true fundamentals of reality are timeless, and that time is a kind of phase of matter, a property that appears under certain cosmic conditions, much like liquid water appears from individual H2O molecules. It's a convenient and powerful framework that allows the universe to complexify and evolve, but it may not be part of the ultimate bedrock of existence. This doesn't diminish time. It makes its existence and consistency all the more marvelous and worthy of exploration. This concept of the universe as a vast information processor leads us to one of the most captivating analogies in modern physics, the idea that the cosmos itself might be functioning like a colossal computer. In this view, the edge of the universe isn't a cold, barren wall. It transforms into the ultimate processing unit, the cosmic equivalent of a central processor or a vast memory bank. Imagine the entire observable universe as the output on a magnificent screen, and the cosmological horizon is the intricate circuitry and code running the program. The steady, reliable flow of time we experience isn't a fundamental given. It's the processing speed, the clock rate of this grand computation, a rhythm generated by the constant churn of information being crunched at the boundary. This isn't just a poetic metaphor. It's a framework supported by serious theoretical work in fields like digital physics and the hypothesis that the universe is, at its heart, a quantum computer. These theories propose that the most basic level of reality isn't made of tiny strings or particles, but of bits, binary units of information. Space, time, matter, and energy are all emergent properties that arise from the ceaseless manipulation of these fundamental bits, a cosmic computation of unimaginable complexity. To grasp how this could work, let's scale this immense idea down to something more familiar. Think about the computer or phone you're using right now. At its core, it operates on a simple binary language of ones and zeros. Through layers of complex software, this binary code translates into the rich, interactive experience you see on your screen: videos, games, text. The device itself has physical limits, its processor speed, its memory capacity. Now, expand that concept to a universal scale. The universe's boundary could be acting as that fundamental processing surface, operating on its own kind of cosmic code. The laws of physics, the rules governing gravity, electromagnetism, and quantum mechanics aren't just discovered laws. They could be the universe's operating system, the programmed software that dictates how information is processed and reality is rendered. In this model, the arrow of time emerges naturally as the direction in which this computation unfolds. The past is the data that has already been processed and stored, while the future represents the potential states yet to be calculated. Our experience of a flowing present is our localized perception of this computation happening now. This computational perspective offers a stunningly elegant solution to the puzzle of time's origin. If the universe is computing itself into existence, then time doesn't need a separate, mystical beginning. The initial conditions of the Big Bang could be seen as the initial input, the first line of code booting up the system. The subsequent expansion and evolution of the cosmos is simply the program running, calculating each new state from the previous one. The edge of the universe, the cosmological horizon, plays the critical role of the active processing layer where this calculation occurs. It's the surface where the quantum bits of information are manipulated, where the probabilities of quantum mechanics collapse into definite states, and where the next moment in time is literally computed into being. This turns the traditional view completely on its head. We are not living inside a pre-existing container of space and time. We are living within the output of an ongoing computation, whose processing core is the farthest reach of reality itself. Our entire timeline, from the Big Bang to the distant future, might be the result of a single, unified calculation happening at the boundary, making the edge the most dynamic and creative place in all of existence. Yet for all its elegant symmetry, our lived reality is stubbornly one way. We remember the past, not the future. A shattered glass reassembles in reverse only in our imaginations. This undeniable directionality is what physicists call the arrow of time, and it stands as one of the most profound puzzles in all of science. If the fundamental laws are symmetric, where does this overwhelming asymmetry come from? The answer might be found not in the laws themselves, but in the unique conditions of our universe, conditions that could be dictated by its outermost edges. This is where the concept of entropy becomes absolutely central. Entropy is essentially a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system can never decrease. It can only stay the same or increase over time. This is the scientific reason your tidy desk inevitably tends toward mess, why heat flows from a hot cup of coffee to the cooler room until everything is the same lukewarm temperature. This relentless march toward higher entropy, toward greater disorder, gives us our most familiar arrow of time. But the second law doesn't explain why entropy was so low to begin with. It simply states that once it's low, it has to increase. So the real mystery is why the universe started in such an incredibly ordered, low entropy state, a state as exquisitely improbable as a perfectly stacked house of cards. This is where the universe's edges enter the story as the potential architects of asymmetry. Think of the cosmic boundary not as a passive wall, but as an active constraint, a condition that sets the rules for the entire game within. Imagine a vast, calm ocean. The fundamental laws of fluid dynamics are time-symmetric. A wave breaking on the shore would look just as physically valid if played in reverse. But the boundary of the ocean, the shoreline, imposes a drastic asymmetry. The wave crashes onto the beach and dissipates its energy. It doesn't spontaneously gather energy from the sand and surge back into the ocean as a perfect wave. The boundary condition breaks the symmetry. In a similar way, the edge of the universe could be acting as the ultimate boundary condition. If the state of maximum entropy, of final equilibrium and disorder, is defined at the cosmological horizon, it creates an immense gradient. The entire interior of the universe is then driven toward that state, like a river flowing inexorably downhill toward the sea. The low entropy of the Big Bang was the universe at the top of the hill, and the edge of the cosmos is the sea level toward which all disorder flows. This relentless flow is what we experience as the direction of time. This elegant idea connects the impossibly large to the intimately small. The microscopic laws that govern atoms and photons are perfectly comfortable running backward. But when you have a system with a specific boundary condition, like the edge of the universe mandating a state of high entropy, it forces all those tiny, reversible interactions to collectively conspire to produce a large-scale, irreversible flow toward disorder. The boundary at the edge imposes a global arrow of time that emerges from the cumulative behavior of countless time-symmetric events. This means the reason your coffee cools and you can't unscramble an egg isn't just a local rule. It could be a direct consequence of the ultimate boundary of reality itself, a cosmic directive written at the frontier that gives time its universal and irreversible direction. So we've journeyed to the very edge of thought itself, exploring an idea so profound it reconfigures our place in the cosmos. We began by dismantling the ancient intuition of the universe as a closed container with rigid walls, and instead we imagined its boundaries as vibrant, active interfaces, dynamic membranes where the most fundamental processes unfold. From the holographic principle, we learned that our entire four-dimensional reality, rich with history and possibility, might be a magnificent projection from a two-dimensional surface at the farthest horizon. This isn't science fiction. It's a serious proposal that the edge of everything acts as the ultimate cosmic hard drive, encoding the information that manifests as our flowing timeline. We then saw how this connects to the relentless arrow of time, guided by the inevitable increase of entropy. This isn't just about things getting messier, it's about a cosmic gradient, a flow of disorder from a beginning of exquisite order toward an ultimate equilibrium at the boundary. The edge sets the condition, and the entire universe flows toward it, giving time its irreversible direction. We ventured into the quantum realm, where the seething vacuum near these frontiers bursts with potential, where virtual particles are ripped into reality, suggesting that the raw material for time itself is being forged in the quantum fires at the perimeter. And we considered how the mysterious force of dark energy, stretching the very fabric of space, might be the engine that is actively manufacturing new moments from the expanding frontier. This perspective is nothing short of a Copernican revolution for time itself. We are not living inside a pre-existing container of space and time. Instead, we are within the output, the interior experience of a universe that is computing itself into existence, with its outermost edge serving as the processing core. Time is not a fundamental stage, it is an emergent story, a narrative generated by the cosmos at its farthest reaches. This transforms the edge from a silent, barren limit into the most creative workshop in all of existence, the engine of chronological innovation. While countless questions remain and the debates are far from settled, the converging evidence from black hole physics, quantum mechanics, and cosmology points compellingly toward a universe that writes its own rules at the frontier. I'd love to hear how this changes your own perception of time. Does it make each moment feel more precious, knowing its origin might be tied to the most distant reaches of reality? Share your thoughts in the comments below. If you enjoyed this mind-expanding journey to the edge of the universe, be sure to like this video and subscribe for more deep dives into the greatest mysteries of space and time. Thank you for watching.